Get started. It's a pleasure to have Jerry Mitrovica back at Stanford. I say back because I'm trying to remember something on the order of 3 years ago. Jerry was here to give a department seminar and gave a fascinating discussion about sea level rise. It might be that as glaciers melt, that water is distributed uniformly around the globe. And as Jerry so nicely pointed out, that's not at all the case. And in fact, sea level will rise in some areas and fall in others, depending on the source of the water. And it gave rise to this idea of sea level fingerprinting. The idea that by looking at where sea level goes up and down, you could actually determine the source of the water. So today he's going to tell us a little bit more about sea level. He has a very intriguing title, which I'll let him explain in the course of his talk. I should point out that sea level is very much in the news these days. What I've gleaned from the New York Times is that this intergovernmental panel on climate change is about to release a report, and the sticking point seems to be, in fact, predictions of sea level. How much the report is going to state the range of possible sea level rise. And so I guess we'll all have to wait until the report is released. So a bit about Jerry. He did all his academic training at the University of Toronto, undergraduate and PhD, and then took a brief interlude to the Smithsonian Harvard Center for Astrophysics as a postdoc before going back to the University of Toronto in the faculty, where he's now the J. Tuzo Wilson Professor. Jerry has received a number of awards, including the Augustus Love Medal of the European Geophysical Union. He's a fellow of the AGU, and the list goes on, but I won't go through them all. So we're very fortunate to have Jerry here, and looking forward to hearing about the search of lost time, ancient eclipses, modern satellites, and the enigma of global sea level rise.
Great, thank you very much. Yeah, it's wonderful to be back. I always seem to be back here when I'm on sabbatical at Berkeley, so it's time to take a sabbatical at Stanford, I think. So, so that's a hint to people around here to invite me to do a sabbatical. The work I'm going to be, there will be some overlap in what Paul was just talking about. I wanted to go through some sea level fingerprint work as well as some of this. I knew that would happen. Amy? Okay. This work is done in collaboration with John Warr and his group. Archie Paulson was his graduate student now at Berkeley down the hall from me. And my group is Samu Matsuyama, who's now at Carnegie, and Mark Tamassi, who's at the Smithsonian. But collaboration is really the wrong word for it. It was a sort of a unique event in my kind of experience as a scientist. John and I showed up at the same conference, giving the same talk on the same topic, same ideas, looked at each other and thought, do we rush to print or work together? And we worked together. And that's very unusual in this field, which is more competitive than is healthy. We ended up writing a whole series of joint papers. My main goal at Berkeley is to write a review article on Earth rotation, some work that I've worked with John. The background of this overhead is not a PowerPoint option, and you can sort of barely see it, unfortunately, but it is, in fact, a blow-up of an image from a Babylonian tablet dating an eclipse to about 2,500 years ago that I'll be talking about really more in the second half of the talk than the first. So there is no serious scientist who studies global sea level rise who does not believe that in some average sense over the last century, sea level has risen by a couple of millimeters per year. That is widely accepted and widely agreed upon. But that number raises two really fundamental problems. The first concerns geometry, that I talked about a little bit last time I was here, but I'll expand on. And the second is amplitude of that rise. In terms of geometry, what we see is that if you go from place to place around the globe, you notice, and you look at tide gauge records, I'll explain what those are. Sea level actually changes in a geographically highly variable way. Some places 5, some places 1. The average may be 2. But why is that true? For the longest period of time, including on websites of climate change deniers, the idea that you could vary sea level was an argument against polar ice sheet melting. The view was that if you melt an ice sheet, sea level goes up like the bathtub model, more or less uniformly. So that variability was considered to be a very important obstacle to getting people to accept the origin of that rise. The second problem was posited, he called it an enigma, by Walter Munk in a very influential paper. So this is a more serious concern, let's say, that Walter raised. He showed that there are a series of rotational observations or data sets on Earth that are very well reconciled, fit almost perfectly by a model of the ongoing adjustment to the Earth to the Ice Age. This is to the glacial cycles that ended around 5,000 years ago. Munk showed, and even I was perplexed when I read this paper, that if you just look at models of the Ice Age, and I create models of the Ice Age, you can predict these rotation observables almost perfectly. That leaves no residual. If you have 2 millimeters per year of sea level rise that's coming from the melting of polar ice sheets, that melting will have very strong signature in rotation. But according to Munk, there's no room in the rotation observations to fit that signal. And so this has become known as the sea level enigma that we're going to solve today. It's actually taken 5 or 6 years of hard work to understand what the resolution of that problem was. So, well, that's not surprising given that Munk came up with it. In all of what I'll be talking about, whether I'm looking at sea level or rotation, the main underlying theme is the first step. I'll talk about the enigmas, I'll introduce them, I'll show you the data sets, but the first step is to apply a correction for glacial isostatic adjustment, that is for the Ice Age. So I need to give you just a 5-minute ultra-short course on Ice Age geodynamics, it's known, give you some examples of observables that are related to this. We know that the last million years of Earth's history, even more, but the last million years have been characterized by a series of glacial cycles, each with a period of about 100,000 years. Within each cycle, there's been a slow glaciation or growth phase, followed by a much more rapid, glaciologists would say catastrophic deglaciation event lasting anywhere from 5 to 15,000 years. This is an image of the, or a plot of the average sea level change over the last glacial cycle. So as you grew these ice sheets, sea level went down about 120 meters and then it came back up much more rapidly. The Ice Age, for all intents and purposes, ended at around 5,000 years ago. The plot at the top here represents an image of ice cover at last glacial maximum in the northern hemisphere. So around 20,000 years ago, when we're right at that point, when the ice reached its maximum extent, you have major ice sheets that reached 3 kilometers or so over Laurentia, Cordillera. Greenland was much larger than it is today. The ice sheets over Greenland, West and East Siberia, even Scotland. I tell a story of being at a European meeting. I might have told it 3 years ago, and calling Scotland the northern tip of England, and 10 people walked out of my talk. So I have to be very careful to say that's Scotland. That is not the northern tip of England. So from 20 to 5,000 years ago, we went from here to here, sea level rose 120 meters. That was so significant, so massive a mass redistribution, so recent, the Earth is viscoelastic, that the Earth remains in a state of isostatic disequilibrium. It remains in a state of adjustment. It's affecting all sorts of observables. And the formal name for it, and I'll say GIA, but is glacial isostatic adjustment. So the first thing we have to do is start correcting all of these observables for this effect. So I wanted to just go through some of these with you. The first very common data set associated with GIA, or the Ice Age, is gravity. This is a figure taken from a paper that we've now revised and resubmitted to Science. We hope it comes out very soon, using gray satellite gravity data to measure rates of change of gravity, not just gravity or static gravity, the rate of change of gravity over North America using this gray satellite. Now, there have been maps of the static gravity field. I was just talking to Norm Sleep about this a little bit. There have been maps of the static gravity field for a long time, but the static gravity field, which was associated with the Ice Age, but the static gravity field can be contaminated with a whole host of things, crustal heterogeneities. I've even written papers on how much of the static gravity field may be due to an interaction between mantle flow and the lithosphere. But the time rate of change, this is the first ever map of the time rate of change of gravity, and that is definitely an Ice Age signal. That is definitely ongoing adjustment. It's more than that. it's actually resolved a very long-standing debate in the literature amongst glaciologists, some of whom believed that the Laurentide ice dome was just one monodome, and others who believed there were two domes, west and east of Siberia. And this, I think, proves that this was a multi-domal ice sheet, right? Because gravity and the rate of change of gravity has very high spatial resolution, so out comes a sort of the ghosts of the ancient ice sheet, as Mark Simons has called it. So this is one observable that's reflecting the ongoing uplift of Laurentia after it was unloaded. Another that will have more relevance to this talk are changes in rotation. If you're moving mass around, you're changing ice, water, you're deforming the Earth underneath, you're changing the inertia tensor of the planet. If you're changing the inertia tensor of the planet, you conserve angular momentum, something's got to give, the rotation axis changes. The amplitude of the rotation changes, that changes the rotation rate, and the orientation of the rotation axis changes relative to the surface geography. This is true polar wonder. Okay? This is a plot, an old plot from a 20-year-old paper, 25-year-old paper, showing data from the International Latitude Service, mostly astronomical observations, well, all astronomical observations, the last, well, from here on, all VLBI observations, but it cuts off in 75. And it just shows the pole position over the last 100 years. So we're seeing this true polar wonder. What we're seeing in the short term is, of course, the Chandler wobble and the seasonal variations in the pole. And there's even a 7-year effect, which is just the beating between those two. But I don't, although I've studied the Chandler wobble and written a few papers on it, my interest today is in this long-term trend, which shows over this period, the pole has been drifting slowly towards Hudson Bay. This led a lot of people to believe, because basic physics tells you if Hudson Bay is going up, and Hudson Bay is the main deglaciation center, the pole should in fact be moving towards Hudson Bay. So people have associated the signal entirely with ice age effects, right? But I put a question mark there because looks can be deceiving. That physics, as Richard Feynman said, right? Some physics can be very misleading, and it was in this case. This is not due to the ice age. This is due to in a large part due to melting of the Greenland ice sheet. The other, the most abundant observable related to glacial isostatic adjustment, to ice age effect, are these worldwide distributions of late Holocene sea level curves. You see them everywhere. This is in my Canadian neck of the woods. In Hudson Bay, a picture from James Bay, where you see this very characteristic pattern of strand lines. This region is popping up, even today, by a centimeter per year. So a beach formed, the process continued, the next beach formed, the process continued. And so whenever you fly over James Bay or Hudson Bay, at every shoreline you see these parallel strand lines. You see them also in Scandinavia. Why the beaches are discrete features, I'm not sure. I suppose because they're created by sort of unusual storms. But nevertheless, you get these patterns which show this post-glacial uplift. The uplift, in sea level terms, produces a sea level drawdown or fall locally. So here, this is just a very quick pass through some of the observables related to glacial isostatic adjustment. When I introduce each of these enigmas, I'll give you some more detailed discussion of the physics that's relevant. So let me look at this Enigma 1 that I talked about, the geometry. If you look at tide gauge records, tide gauges are very low-tech devices. Think of them as cylinders with a ping pong ball that acts as a float. As the sea level goes up and down, so does the ping pong ball. You have some measuring device. I just took this stuff off the web. Tide gauge is always connected to some land-locked or land-based marker, in this case some kind of pier. This is a picture of a tide gauge site in Western, this is England, not Scotland. I have no idea what these arrows point to. I think that's just a toilet or something, right? But that's a tide gauge installation. That's the actual tide gauge. That's a recording device. You have literally thousands of these. But you don't use many of them, as we'll see, for global sea level rise studies. But you have thousands of these distributed around the globe. In some cases, for example, in Sweden, where geodesy is a high form of art, these tide gauges have been recording for hundreds of years, 270 years. Is the oldest tide gauge record, I think, right? So we get these tide gauges, but the weird thing about them is they show this variability. Impossible for you to read this, but I'll tell you what this is. This is about 100 years, and this is about 300 or 400 millimeters. And this is tide gauge records in Sweden, Finland, I have to even remember these, the UK, Portugal, the US, and Canada. Yeah, there's a Canadian site, which I actually kludged on, which is great right? It didn't actually exist in the original plot, but I wanted a Canadian tide gauge, right? So there's this long-term trend through them. So you get both tidal variations, oceanographic variations. A short period of tides are filtered out of this, of course. And what you get are these long-term trends. In some cases, sea level is falling. In other cases, it's staying relatively constant. In other cases, it's going up. What's going on? Right? This is a typical plot you see in sites of people who are trying to deny a connection to climate change. Because the argument is these should all be pointing in the same direction, right? Okay? Well, if you're sophisticated, you would say, well, wait a minute. And this is what people did for several decades. The first thing I'm going to do here is I'm going to correct this for ice age signal. Because I've just shown you that the ice age, which ended 5,000 years ago, is producing an effect on all of these tide gauge records. Right? And so I have to go in and correct them. And the hope is that they'll all then line up. They don't, of course. So now what I'm going to show you is that correction. So this is sort of a state-of-the-art, almost state-of-the-art correction that you would apply to the tide gauges. This is a numerical prediction. There's no data here. Well, there's data underlying the models here. But this is a prediction of the present-day rate of change in sea level due to the ice age, due to this ancient process that ended 5,000 years ago, right? So it has nothing to do with modern melting, right? This is ongoing effects associated with a process that ended 5,000 years ago. The Earth is viscoelastic. It is still deforming. So I was going to go through a really detailed physical discussion of this, but I can really abbreviate it. This is taken from a paper, a review paper that I wrote with one of my former graduate students that was in particular focused on this, what we call the far field, this equatorial band here. So this color scheme really saturates outside that band. So let me break it up into near field, the blues and reds, and this far field, and try to give you a sense of what the physics of this plot is. Okay? Well, in regions that were once covered by ice, not here, I pointed this out, well, Patagonia, the Antarctic, those regions are post-glacially uplifting, just as I showed you that picture of parallel strand lines. They're uplifting at rates of about 1 centimeter per year, and sea level for a geophysicist like me is defined as really the thickness of ocean. So it's the height of water relative to the land. So if the land is going up by 1 centimeter per year, it means sea level is more or less falling by 1 centimeter per year. Because that's what geology tells us, right? Sea level records are tied to land, right? And so we have to model the same thing. So these are regions in which sea level is falling by a centimeter per year. This is a plus or minus nearly 1 millimeter per year. So we'd be right down the hole there on this scale if I used them, right? Surrounding this region, this blue, that's called the peripheral bulge. When we produced a depression over Canada, we produced a peripheral bulge. I'm spitting on the first row of the audience. Sorry about that. That's why the first row is gone, right? Good. Did you know that? Did somebody email and say he spits? Right? So you've got this peripheral bulge. Can we edit that from what you've got this peripheral bulge around the outside. So when this comes up, this post-glacially uplifts, the peripheral bulge subsides. And since the ice sheets reached near the continental margins, much of these peripheral bulges are on the oceans. Now, just as we're uplifting, we're subsiding, the land is subsiding. So in those zones, we're predicting a sea level rise that can exceed several millimeters, so you'd be down the hole that way, right? This is a global effect, obviously, right? You can't just assume that these sea level changes due to the ice age are localized close to the ice sheets. They extend well away into the peripheral bulge and even further. So now what is all this? This yellow here wasn't really understood despite 25 years of numerical modeling until about 3 or 4 years ago. Certainly it came out of the models, but the physics was unclear, right? And it's really just a conservation of mass. Think of it this way. So what are we seeing here? We're predicting an equatorial band of sea level fall on the order of 0.5 millimeter per year due to the ice age. And the reason for that is, as these blue regions, these bulges subside, water has to enter into those regions that is vacated by this subsiding bulge, and the whole level of the ocean just draws down. The analogy I use is, think of an Olympic-sized swimming pool. You have some object submerged at the end of that pool. I'm going to be Canadian and say a hockey puck. So you've got a hockey puck submerged. I'm standing at this side of the pool. You take that hockey puck out. I may be 50 meters away, but I'm going to see the water level just go drop, right? in order to conserve mass. In the same way, as water floods into these bulges that are subsiding, there's a drawdown of water here, 0.5 millimeter per year. That seems moderate. But take a 0.5 millimeter per year, extend it back 5,000 or 6,000 years to the end of the main deglaciation, and you get 3 or 4 meters. And that's important because one of the most endemic geological features, late Quaternary, late Holocene geological features in the Pacific are exposed coral terraces. You can't go anywhere. I was born in Australia, right? And you cannot go anywhere around here without seeing all of these corals that are now 3 or 4 meters above sea level, and they're dated to about 5,000 years of age. So you would not be, well, let's say you would be shocked to be told, sitting there on this beautiful equatorial Pacific beach, that drop in sea level was associated with dynamics of the ice sheet. I guess I have this on a timer, right? That is associated with ice sheet dynamics, right? It's got nothing to do with the usual explanation, which was that it was just some local thermal tectonic effect, right? That the crust was being heated or it was uplifted and all of these corals were being exposed, right? No, right? It's all associated with this process we call siphoning, where water is drawn away, right? And I'm working on some work with Bill Dickinson, who's very interested in the timing of that. Okay, so now let's go back. If I now can use this, I should just say, my goal is to come up with this plot because I want to decontaminate those tide gauge trends. I want to go to modern trends of sea level change, and I want to correct. If I have a site here, a tide gauge site, I go to this sort of plot. I say, okay, correct by this much that trend to get a residual trend, which I would hope is more closely linked to some sort of modern climatic variation. Okay, I said there are thousands of tide gauge sites, but we only use several dozen, right? And the choice of those sites is a great mystery to me. But we were forced by reviewers of this series of papers to choose the ones that others had chosen. So don't shoot the messenger. This is a group of sites that was selected by Douglas that is in common usage. He avoided sites near cities. Lots of groundwater pumping cause crustal subsidence, and your sea level is totally contaminated by anthropogenic effects. Away from, notice, convergent, I should have put this in bold, convergent plate boundaries. He has no problem with transform faults, but away from subduction zones areas, the idea being in those regions you can have a lot of vertical tectonic motion. And he also avoided, and this becomes important later in the talk, tide gauges with records less than 30 years because there are clear decadal fluctuations in sea level. And unless you have 30 years of data, you can't separate the two. We'll see that becomes very important even in the rotation stuff I talk about. So when you do that, here's what you get. Here are the sea level rates you predict at these 24 sites. These are the European sites. New Zealand, sorry, the resolution isn't what I expected here. That's Honolulu, San Francisco, Santa Monica, California, and then towards the US East Coast, right? So they are grouped more or less. You can think of sort of European sites, Pacific sites, and US East Coast sites, okay, generally. So you see this trend, okay? Some show, and this has been really cleaned up. The trends are much larger when you use other sites, but you can go as low as 0.5 millimeter per year, as high as 2.5 millimeters per year. It's not uniform. So now let's apply that correction. So we take all of those rates, these are long-term trends through the tide gauges. Let's now apply the ice age correction to it. And unfortunately, in a statistically significant sense, the geographic variability gets worse, not better, right? And so this left everybody in a perplexed, right? I'll try to spit in this direction. What we to make of it? Well, the first thing you do is you just take the average and you publish a Nature paper, I guess, right? So you take the average through here and you come up with an estimate of 1.5 millimeters per year, which is not so bad, actually. It's a pretty good number, even today. This study was just done a few years ago, but most people agree. And this variation was just a mystery that Douglas coined the term geophysical noise for it, right? But we can see that in that noise is something very beautiful. In that noise is the key to unlocking not only how much sea level has risen, but where that water came from, right? This is something that people never expected to be the case. You can actually look at that variation and you can infer from it the sources. of the sea level rise, not simply the average, right? And this is this fingerprint idea that Paul alluded to. I wanted to go over quickly because it has relevance to the second half of the talk. When ice sheets melt, forget the bathtub model, right, which says that sea level will rise uniformly. Ice sheets, just like the sun and the moon, produce a tide on the oceans. Okay? When an ice sheet melts, two things happen. The tide relaxes, right? And sea level rises in some integrated sense. You're dumping water, so if you add up all the water in the ocean, it's increased. But that tide relaxes, and it turns out that that relaxation of the tide, so as you melt from here to here, the relaxation of this tide, highly exaggerated, obviously, that tide, means that in an area close to, and let me just say close to vaguely here, close to the ice sheet, sea level actually falls. And when we published this paper, both reviewers said, that's crazy, right? And when they accepted it, they said, oh my God, it was like we had invented gravity, right? Except when we pointed out that the first paper pointing this out was 1888 by Woodward, who worked at the USGS, or its forerunner, right? What he was doing studying the gravitational effect of melting ice sheets, I don't know. But there's a long history of this being ignored, let me put it that way, right? So simply put, sea level will fall. And this hinge point is not close to the ice sheet. It's 2,000 kilometers away, right? So that's really counterintuitive. And everything I'm about to tell you in terms of tide gauges is equally relevant today, and we do it all the time now. We're monitoring ice sheets, Alaskan ice sheets, for example. So typically you'd say, well, okay, if Alaskan ice sheets are melting, we should be looking around and seeing sea level go up. No, we're actually looking for the sea level to fall near Alaska in order to be a reflection for the melting of those Alaskan ice sheets, right? It's highly counterintuitive, but it's correct. It's Newton's law, right? Let me give you some examples of that. I'm going to show you three numerical predictions, one of melting from Greenland, one of melting from the Antarctic, and one of melting from these small mountain glaciers and ice sheets that Meyer tabulated. So Mark Meyer at, I guess, University of Colorado, or one of the organizations there, tabulated this global distribution of mountain glaciers. So I'm going to just melt those. I'm going to melt uniformly from each of those, and I'm going to ask, what does sea level look like? Let me just use one example for the sake of saving time. Here's a model of what happens. Unfortunately, the color scheme on my laptop has reversed this, but that's okay. This is the model where we've said, let us melt enough from Greenland tomorrow to raise sea level a meter on average. Okay? So we've taken off enough of Greenland. So if the bathtub model was right, you'd see one color. The dark blue here is this zone where sea level is actually falling. Believe me, the bars here are all screwed up for some reason. So sea level is actually falling in this region. So imagine if I told you, I called my friend in Scotland. I don't have any in Scotland anymore, but if I call my friend in Scotland and say, tomorrow Greenland is going to catastrophically collapse, right? He'd be justifiably worried. But he shouldn't be, because sea level would fall in Scotland, okay? In the same way, and it would increase, you pay the price somewhere, so in the southern hemisphere, you have an increase of sea level that's about 50% more than you expect, so the average is about a meter, okay? Well, it's exactly a meter. This is a numerical prediction, right? Different ice sheets, different fingerprints. The question is, can we now combine these things? Can I say, how much of this and how much of this and how much of this will reconcile the tide gauge trends, right? And this is the answer. So here are those raw tide gauge rates. Here now are the rates after you've corrected for the ice age. And this blue line represents an attempt to do a simple least squares fit by adding up melting of the different ice reservoirs that we think are melting. For example, these mean nothing, A, B, C, D, E, but B is melting from Greenland, right? So we have a 0.5 millimeter of melting from Greenland, another 0.5 millimeter from the Antarctic, and D is thermal expansion, because the oceans also thermally expand, and C is from those mountain glaciers. And we get a fit that is, again, in a statistically significant, better than 99% statistically significant improvement in fit relative to this line. So the moral of this is, there is no enigma. If those sea level rates were uniform, I could prove to you they're not coming from that sea level rise that we see in the 20th century is not, you turn the whole thing around. It could not be coming from the melting of polar ice sheets. The fact that it varies, And the fact that it can be fit by these three fingerprints is very strong evidence that it is. And now I think most people ascribe, we'll see what the IPCC report says, but most people subscribe to melting in Greenland of at least 0.5 millimeter per year. And that's necessary, by the way, because European sites show less sea level rise than others. And remember the physics of the fingerprint. If Greenland's melting, its effect on Europe, which is close by, will be much less than its effect elsewhere. So to bring that rate down in Europe, you need to melt off Greenland. So now let's move to the second enigma. This is a much more subtle one in a sense, and it's my first attempt to explain it to an audience. So we'll see how successful this is. This was first described by Walter Munk. It's just published a month or two ago in EPSL. He said, let me recap, there are these three observations. Munk knows everything there is to know about rotation. There are these three observations, and I can fit them very accurately with the Ice Age model. The same Ice Age model that I just showed you that predicts sea level change, let me also use that model to predict perturbations in rotation. So he does that, and he fits all three of these observations. The first is integrated changes in the length of the Earth's day, or integrated changes in the rotation rate that you infer from ancient eclipse records. I'll explain each of these in detail. I'll just go through them now. So that's his first observation. Over the last 3,000 years, we have record of ancient eclipses. We can use that to infer integrated changes in the Earth's rotation rate, number one. Number two is almost like the time derivative of this at the present day. Satellite inferred changes in the Earth's rotation rate over the last 20 years, right? Not 3,000. But satellite inferred over the last 20 years. And the interesting thing about that, as we'll see, is it turns out that this is much less accurate than this is. Right? The people were placing too much confidence on this observable. But nevertheless, that's the second observable Munk used, this rate of change that's seen by satellites that we all learn. I learned about it in my fourth year introductory to geophysics course, using satellites to measure changes in rotation rate. Right? And the third is this long-term change in the orientation of the rotation vector, polar wander. That's inferred from astronomical observations. Okay? Those are his three. So let's look at all three of them in a little bit more detail, beginning with these ancient eclipses. It's really a remarkable compilation published now a decade ago, updated very recently by Stevenson and Morrison. What they did is they looked through a whole suite, catalog. I mean, it took them over a decade to do. Look for records of ancient eclipses. I've really just thrown together a couple of, unfortunately this is not as well focused as it looks on the screen, but that's okay. As many as they could find, look through the literature, just get as many records of primarily lunar eclipses, but some solar eclipses, to get this record back as far as possible. These are, of course, images taken from Chinese records. This is about 1,500-year-old record, or a record of an eclipse that occurred. You can't really see this, but this is quite interesting here. This is a clepsydra. Does anyone know what that's a water clock? So it's just like an hourglass. So the way the Chinese timed eclipses was with a water version of an hourglass. They had water that was filled this bucket and then slowly dripped down the sides. It was well calibrated to measure time. And so that's their timing device. In fact, it was a timing device for many hundreds of years. This is a Babylonian record of an eclipse that's 2,500 years old, and this is the image that, when blown up, is the background of this overhead, right? And so I joke with my graduate student that I would start reading this to you, but I don't know Babylonian, right? This is a book, actually, that published that actually combined the scientific side of this with some really wonderful anecdotes. Okay, you put together all these records of eclipses, what do you get? You get this very well-known curve now amongst the rotation, what would you call them? Geophysicists interested in rotation. This is grouped. The symbols represent Babylonian eclipses, Greek eclipses that also extend into the Babylonian. These are Chinese here and here. I'm not sure why there's a gap in Chinese eclipses. And these are Arab eclipses, right? Measured by Arab astronomers. Now, of course, why were they interested in eclipses? Because for all of these cultures, without exception, eclipses were a harbinger of ominous events, right? And they've always been a harbinger of ominous events. So they were really astrologers in that sense, right? The attempt was to predict the next occurrence of these eclipses. That's why it played so much of an important part in all of these cultures, right? This is a cubic spline fit to the data, but what is it that we're plotting? This is Morrison's choice of an axis label. It's not mine. He calls it the rotational clock error. What this is the following. Let us go to that recorded eclipse. Let's find out when the eclipse occurred, okay, according to that record. Now let's predict when that same eclipse would have occurred if the Earth's rotation rate today stayed constant forever and ever, right? So you've got one thing that's constant, one thing that's not constant, the Earth, right? All sorts of processes are occurring. And he's looking at the time shift as you go back. And so you're integrating back. You'll, of course, be 0 today. You'll integrate back. So the time shift, what he calls the clock error, although I don't use that term, adds up 2,500 years ago to be about 1,600 seconds, or 4 hours, 4 to 5 hours. So this Babylonian eclipse took place 4 or 5 hours with a 4-hour or 5-hour time shift relative to when we think it should have occurred if we assume that the rotation rate was constant. What this records is a slowing of the Earth's rotation rate over that period. Now that's exactly what we expect, because we know that the Earth is slowing because of tidal dissipation, right? Waves crashing, shallow water waves crashing. In fact, more and more literature shows that a lot of tidal dissipation occurs in the deep ocean. So whatever, energy loss through the action of waves and turbulence in the ocean causes the Earth's rotation rate to slow down, right? That's the tidal dissipation effect. And we have an extremely accurate constraint on that. That's one of these things that can be very accurately estimated. Should I say, well, okay, there's a couple of steps. I hope I don't confuse people by this, but if the Earth is slowing down, I'm now going to do this in very quick voice. What does that mean? That means in order to conserve the angular momentum of the system, the moon must be orbiting the Earth at a more rapid rate. If it orbits more rapidly to conserve angular momentum, what happens? It moves outwards. So the recession rate of the moon relative to the Earth is actually an extremely good measure of this tidal dissipation, right? Okay? So we have that. But when we find that out, when we look at what the Apollo astronauts did for us, they put up mirrors on the moon so that we could flash lasers back and forth to get the Earth-Moon distance. When we look at that recession rate, which is about a couple of centimeters per year, we convert it to tidal dissipation, we get this curve, this blue line. And this is very accurately known. And it's a problem, because this means that the Earth is slowing down, but the rate at which it's slowing down is lower than we would expect from tidal dissipation. And this difference is considered to be very significant, and it's known as the non-tidal acceleration of the Earth's rate of rotation. And it is thought to be due, and it is due, to the Ice Age effect. Think of what the Ice Age did. You piled ice on the poles, you flattened the Earth. You got rid of the ice, the Earth unflattened. As it did, it speeds up. Think of the figure skater. I'm the only Canadian alive who hates figure skating, but think of the figure skater, right? I just can't watch, right? Anyway, that's another story, and I don't have time for that. So as it gets more and more spherical, I don't know how anyone can watch that without anti-anxiety medication, because they're always falling. Anyway, so as it gets more spherical, it speeds up. That's a non-tidal acceleration of the Earth's rate of rotation, right? So this discrepancy is associated with the speed up of the Earth as the Earth becomes more spherical, as it recovers from being bulged outwards due to the ice sheets. So that's the number one data set that Munk used. Here's the number two data set. This is the changes in the rotation rate. The geodesists have a better term. They say changes in length of day, right? Which I enjoy for some reason. But changes in the period associated or measured by satellites. This is a hokey image I took from the web of the LEGIO satellite, which is really the primary driver of all of this. But there have been lots of estimates based on now 20 years of combining all of these satellites. And you get an estimate over that 20-year period. This is the typical, what I'll call traditional because it's wrong, but it's the traditional estimate of the change in rotation rate over the normalized change in rotation rate. It's a meaningless number. It's so small, 5.5. What does this mean, 10 to the minus 11 years? What it means is that, and tidal effects have been taken out, it means that there's a decrease in the period of the Earth. So this is this acceleration I talk about when you get rid of the tidal dissipation. Decrease in the period which has now currently 86,400 seconds, of about 3/millionths of a second per year. So the Earth's period changes by that much per year. But remember, this is the change in the period of the length of each day, so to speak. So this effect accumulates rapidly. If you go back in time, it adds up to many hours, in fact. So satellites tell us that this is the decrease in the period over the last 20 years. This is a much more boring observation, but I showed you that nice observation of Chandler wobble, etc. But this is an inference of the wander of the rotation pole with respect to the surface geography. So this is astronomically determined secular rate. This is how that pole is moving slowly, and it's moving about a degree per million year, or million years, or about 11 centimeters per year towards Hudson Bay. Okay, this much per year towards Hudson Bay. Now, superimposed on that are meter-like variations associated with the Chandler wobble. So you have to watch for quite a long time to get an accurate trend. And that's an accurate trend. Okay. Now, just as I did with sea level, I have to go back to Munk and I have to say, what about this effect? What does this have to say about those three observations? If I look at that same model, and I showed you my beautiful color picture, somebody shouldn't call your own pictures beautiful, should you, right? You should wait for other people to say that. But if I showed you those images, I can take those same models and predict rotation perturbations with them. What do I get? Well, what I get is what Munk showed us, a perfect fit. But before I do that, I want to show you, I haven't had to do this in sea level, but I have to do it now. When I model the ice age, I have several inputs. The first is a reconstruction of the ice sheets. And we have that. There's several models you can try that in bulk capture the ice sheet geometries pretty well. And in fact, for rotation calculations, you don't have to have them very accurately at all. It's a long wavelength effect. You don't need the details of the ice sheet, just the bulk size of it. But you also need a model for the viscoelastic structure of the Earth. You need to say, what is the Earth made of, in a sense? How does it respond viscoelastically to a force? Well, elastically, we're fine. We can just use a seismic model like PREM. So we get the full depth variation of the elastic structure. We consider this known, accurate, put it away. But we don't know the viscosity structure of the Earth. And if you don't believe that, you should go to a meeting where they talk about viscosity of the Earth. That's fun. The parameter of particular importance for us here is the lower mantle viscosity. The viscosity of the material, and just as the word implies, if you think of just the general usage, the kind of resistance of the material to flow when a stress is applied, the viscosity of the deep Earth from about 600 kilometers to the core mantle boundary is really the primary parameter in rotation observation. So I'm going to show you predictions of those rotation observables with models in which I vary this free parameter, just to give you a sense of the kind of variation you can get. And this is really where the enigma is defined, so I have to go through this for a few minutes. So this is that first thing. Remember I was talking about the change in the rotation rate of the planet as inferred by satellites. Here's this 5.5 times 10 to the minus 11, or 3/millionths of a second change in the period per year. Okay? That's the observation of satellites. And what I've done here in this solid line is I've simply done an ice age calculation in which I vary that lower mantle viscosity over several orders of magnitude. Okay? I've done the same thing here. Here's a prediction now not of the change in the rotation rate, but of polar wander rate. How much is the pole moving as a function of that same lower mantle viscosity? And I get this weird, and I'll show you in a minute, incorrect prediction. But this is the traditional prediction, 30 years of predictions that look exactly like this. So Munk looked at these, and he said, wow, if I pick this model, which I'll call GIA1, I could call it GIA Munk, right? Which has a lower mantle viscosity just slightly in excess of the shallow mantle viscosity, but it really doesn't matter for this talk. He picks a model, and he says, look at that. That model perfectly fits the satellite constraint. Perfectly. So that model predicts the change in the period that satellites have seen for the last 20 years. That model also predicts the true polar wander rate that is roughly in accord with the degree per million years we see. And it isn't just the rate. This is a plot of the direction of the prediction. So Munk showed this. This is taken from Munk, essentially. Here's the observation towards Hudson Bay, and that solid line has an amplitude equal to this. but its direction is totally in accord with the observed direction towards Hudson Bay. So he says, this is looking really good. Now let me look at the eclipse data. And so he does that. This TD line here represents that tidal dissipation. Remember, it's the slowing of the Earth that we predict on the basis of tidal dissipation. And these are the observations of the eclipses. My attempt to put error bars on the observations that you saw in the earlier plot of Stevenson and Morrison. What it's done here is he's taken the tidal dissipation. Well, I've actually done these calculations, but I'm using Monk's preferred models. And I've added an ice age effect to it. I've added the effect of non-tidally accelerating the Earth associated with the same model, and I go right through the observations. So Monk called this a remarkable triple accord that cannot be denied, right? And he said there is no room here for a signal due to melting of polar ice sheets. This is all the ice age. Well, how big a problem is that? What is the size of the signal that you'd get from melting polar ice sheets today? Well, there'd be no signal here, because this goes back 3,000 years. You'd only be perturbing the last 100 years. But there is a whopping big signal here that cannot be denied. Here's the same plot I showed earlier, a prediction of the ice age effect as a function of the lower mantle viscosity. Here's the model that I said fits. This bar here represents the signal that is associated with melting 1 millimeter per year from some combination of the Antarctic and Greenland ice sheets. Doesn't matter which. They're both at the poles. They add up to it doesn't matter whether it comes from one or the other. So if you melted 1 millimeter per year from the Antarctic and Greenland, that would be your signal. And think about it. Think about the opposite of the figure skater analogy I told you. If you're melting from the polar ice sheets and you're putting it into the equator, you're slowing the Earth's rotation rate, right? Because you're bringing mass from the pole to the equator. That signal, if you added it to the ice age signal, would just put you well out of accord with the observations, right? This little arrow is associated with the melting of small mountain glaciers, and this I just pulled off the web, right? Here's this other thing. This is true polar wonder. Remember, here's the observation. Here is the prediction using Monk's preferred model. Here is the signal in polar wonder if you melt 1 millimeter per year from Greenland, right? There is no way you could add this signal to this GIA signal and get anywhere near the observation. Monk knew this, and he said there's no room for these signals, right? There cannot be a melting from polar ice sheets, right? So where does the 2 millimeters per year come from? Well, the only other option is it comes from just thermally expanding the ocean, right? But the heat budget of the ocean is nowhere near enough. That's, everybody believes now, to produce 2 millimeters per year. So here's the enigma. Where is it? Well, it turns out there's two parts of the resolution. That's why it took John and I 2 years or 3 years to solve it. The first deals with this uncertainty. I'm going to show you that the satellite data is much more uncertain. In fact, we don't really know what the satellite change in the long-term trend is of the Earth's rotation rate. That's real. I'm trying to be kind of careful here, but if I've had a beer, I'd say we don't know at all, right? Even though I'm going to show you an error bar. The other thing is in this prediction. This is where Norm Sleep and I were talking about it. I could give, and would love to give another talk on how this prediction is done. What underlies the rotational stability of a planet when it's loaded? I can only give you kind of a physical feeling of it, but the mathematics is even more beautiful, right? But it turns out that this prediction, and all predictions like it for the last 50 years, have been wrong. And really wrong, right? They got the theory wrong. So a mixture of data and theory problems get you out of this enigma. This is my very quick and dirty attempt to try to explain. I won't even use this plot. I can explain it in words on why this is too constrained an estimate. Satellites have only been looking for 20 years, even less really, of usable data. Okay? Remember I told you about the tide gauges. I said we really need 30 years of data to get rid of decadal fluctuations in sea level. There is a very large signal in rotation, in the change in rotation rate, that has a very long period that has nothing to do with the ice age, and that's the 18.6 year tide. So there is a tide, there is a long period tide with its period is 18.6 years, which has a whopping large signal in the change in the rotation rate. I don't know how many of you have done tidal theory, but there's 12-hour tides, there's diurnal tides, 24-hour tides, and there's this series of long period tides, 14 days, 1 month, 6 months, 18.6 years, etc. All of the long period tides, because they cause a flattening, an oscillation in the flattening of the Earth, produce a change in its rotation rate. This prediction, for 20 years, since Legios was put up in orbit, all of the software assumed that that 18.6-year tide was precisely known. In fact, the assumption, well, originally it's very good, interesting. You look at the documentation, and it says, this is what we'll use for the 18.6-year tide, but this could be wrong. But everyone forgot the comment, right? And from there on, it was considered to be perfect, okay? But it isn't perfect. It's not perfect because the 18.6-year tide is affected by inelastic effects. We also don't know the response of the Earth at that 18.6-year band. So the admittances between forcing and response that's the only sample we have, that tide. So we know very little. And we don't have a long enough time series of satellite data to separate the two. So the moral of the paper that John and I wrote on this was, you have to wait at least another 15 years until you separate out using satellite data accurately. So in other words, you have to wait 30 years, just like Douglas told us we should wait for the sea level, before you can accurately separate out the 18.6-year tidal effect from any long-term trend, which is what I'm interested in. Right? When you use, and what we did is we played with different models of the 18.6-year, we played with the data span. You know, we're just trying to see how much you converge. We played with 2 different people's models of it all. And a very, would you call it a conservative? I forget how that term would work. But the error bar becomes much larger, and in fact, it's probably double this size. We're just being a little bit careful. Well, we're being a little, I don't know what we're being here, optimistic, right? The 18.6-year tide isn't known, so the goal of, or and it's nice to see that there have been 2 papers published in the last few months that really argue for the same thing, right? That essentially we don't know the long-term trend in rotation rate from satellite data at all, so leave it alone and wait 10 years. The next effect, and I'll be done in a few minutes, I know I'm going over time, is this rotation. I said you don't even want me to put down rotation theory here. But I want to give you a flavor of it. Why were those rotation predictions wrong? Okay, if you want to know what the stability of a rotating planet is, and I'm at Berkeley in part in order to apply this idea to the long-term stability of Mars and its rotation. But if you want to understand the stability of any rotating form, right, you need 2 things. You need a theory that tells you how that flattened planet, because it's spinning and it's flat, how will it deform when a load is applied to it? And as the pole moves, how will it deform when the centrifugal potential changes? So you need to have a theory of deformation. But there's also one number in that theory that appears that tells you what is the background form of the planet. What is the flattened form? What is the flattening of the planet, so to speak, right? Why do you need that? Well, a planet that is more spherical is less rotationally stable. And that should make sense. If a planet is a perfect sphere, its 3 moments of inertia essentially are equal at a perfect sphere. So a little load can cause things to go haywire. The pole can move all over the place. The flatter you make it, the more flying saucer-like you make it, the more stable it will be to that load, right? You will not be able to cross the maximum and intermediate moments of inertia. And so the planet stay, you know, you might see the flying saucer wobble, but you're not going to see it flip, right? Okay? As easily as you would see a sphere flip, okay? Okay, what did the old, so I'm going to focus on that second point. In the old theory of rotation of planets, and in any theory, you need an expression for this background form. This is the way it was done in the old theory. They just said, we have an Earth, it has a lithosphere of 100 kilometers, let's say. Let's assume, this isn't the terminology, but effectively, let's assume the Earth is one big water-filled balloon, and the thickness of the elastic shell around that balloon is 100 kilometers. And it's not rotating, so it's a perfect sphere. This is just Clairaut's theorem, actually, for those of you who've done that in. Now I just spin it up. I now spin that balloon up to the current rotation rate of the Earth, and I ask, what is the equilibrium final shape that that planet will have, right? And it comes out to something like this, and you can get it from Claros theorem, or if you use a higher order theory, and there was one published in the 80s by Naki Boglu, you can get a slightly more precise answer for it, right? So you get that. And that was what was implemented in the theory for the rotational stability. But that's not how the Earth works. You can ask a simple question. What does the flattening that this tells you or gives you, how does it relate to the actual flattening of the Earth, which we know very accurately, right? They're off by about 1%. And everyone thought, who cares, 1%, right? The Earth's flattening is affected, first of all, the Earth's actual flattening does not care about the shell, the lithospheric shell, because over billions of years, any stresses in that lithosphere will relax. And so the first calculation should be to get rid of this shell and just assume that the balloon has no, essentially an infinitesimal elastic sheath. Because we have plate tectonics, because the lithosphere isn't perfectly elastic. In fact, the time scales, my graduate student here, Amy, is looking at the time scales of deformation of the lithosphere, and you can't get much longer than a few 100 million years. So it will have relaxed. The lithosphere isn't there for this purpose. But there's another effect, and that is that the Earth has an excess ellipticity that we've known about for years, associated with convective flow in the interior. Mantle convection is making the Earth flatter than even this balloon with no lithosphere would give you. And I want to give you one image of that. This is a plot that I first looked at 20 years ago of long wavelength seismic heterogeneity in the deep mantle. This red region under Africa, this red region under Pacific are anomalously slow material uprising megaplumes. As they uprise is the wrong word, as they move upwards in the mantle in an antipodal sense, they act to deform the Earth. They act to make the Earth flatter than it should be, right? Just by a little bit, okay? Now you might think, well, this is all theory, except they not only flatten the surface of the Earth, they flatten the core mantle boundary. We have a very nice constraint on the flattening of the core mantle boundary from people like Tom Herring, Carl Gwynn, Bruce Buffett, and others who looked at this so-called rotation anomaly called the free core nutation. So we already know that the Earth is flatter than we would have expected it to be, and it's flatter because of this convection signal. So let me go back and say that this Earth of ours is actually flatter by about 1% than this balloon experiment. And so you'd think, well, so what? Except in the theory, the term that governs this flattening is a term that is something like 1 over 1 minus the flattening over 1, where the flattening is normalized. And the flattening is near 0.999. So if you make an error of 1% on that number, I'll write it here so that you can get a better sense of it. So you have 1 over 1 minus, and let's call this the oblateness term over 1. And this is near 1. If you make a 1% error on that, you can make hundreds of % error on the stability. And that's what you do. You actually, because you use a more spherical Earth than exists, the stability of the Earth, or you underestimate the stability of the Earth by a factor of 3. Right? You underestimate it. So now let's go. This is my second last overhead. This is the new theory. To give you an idea, remember this plot? This was Monk's preferred Ice Age model, predicted using this old loading theory. So now let's improve the loading theory. Let's take into account the actual flattening, not your predicted balloon flattening. And that is the true polar wander rate. It's reduced by a factor of 3. Right? And this is now being reproduced by 3 other Ice Age groups, people who do Ice Age theory. Right? This theory was just wrong. This reconciliation was a red herring. Right? And you can also see this stabilization on this plot where I showed the rate of polar wander, the rate of motion as a function of lower mantle. Here's the old theory. Here's the new theory. So that old model that Monk preferred, you reduce from nearly 1 degree per million years to about 0.3 degrees per million years, nowhere near the observation. And so now it becomes easy to resolve the enigma, right? Because now let's look at the actual observations with the much larger uncertainty in the satellite constraint. We have the eclipse data, which is really unchanged, and a new rotation theory. These are predictions where we take an ice age model, we add to it a model of modern melting. Now we have modern melting, about 0.4 millimeters per year from mountain glaciers and nearly a millimeter per year from the Antarctic and Greenland. Actually evenly split between those two. When you do that, if you take into account now this lower bound, you can fit the satellite constraint because it's really a not constraint. The eclipse is unchanged because it goes back 3,000 years, but the polar wander can now easily be. In fact, you might say that because the ice age produces such a puny effect on polar wander, you need something else. There is now a necessity for a modern signal to fit this, right? So this was a much more subtle enigma to resolve than the fingerprint one and the geographic variability, and it's formed from a theoretical error and an error in the analysis of data. Okay, so here are the conclusions. There have been these two obstacles that are overcome, as I've said, and I wasn't exaggerating. You can just do some Google and Google sort of climate change, sea level arguments against or deniers, and these two enigmas always are in the top 5 or 6 that people use to argue that this could not possibly be, what we're seeing could not possibly be from the melting of polar ice sheets, right? Well, the geographic variation is exactly what you expect from the melting of polar ice sheets, and with this combination of reanalyzing satellite constraints and applying a much more accurate rotation theory, we can also resolve the other. I think I'll stop there. I had some ideas, some discussion of future work, but if it comes out in talk questions, I'll take the opportunity. So thank you very much.
So for all of us that thought that sea level rise had nothing to do with the continental boundary, I'm sure you have a few questions. Newcomers to this seminar know I always like students to go first.
How well do direct measurements of the amount of melting in the poles and the glaciers fit with the amount you need to put in your model to make it work?
Yeah, well, you had Isabella here. So Isabella and Valaconia is part of John Moore's group. And our group, we've looked at mountain glaciers. The problem is that, for example, Grace estimates of modern melting of these ice sheets are going to be probably going to be larger. This 2 millimeters per year is a 20th century average, but nobody does this. Currently, we're probably up to 3 to 4 millimeters per year. So you have to take that into account. So over the Grace time window, for example, we wrote a paper that was published on the Alaskan ice sheets using Grace, and the estimates of Alaskan melting are 3 times larger than Meyer's tabulation from the 80s. That was over a much longer period. So there's a caveat that has to be placed on your question. But within that caveat, fine. The Grace data that we've looked at both for the Antarctic and Greenland could be fit within this model pretty nicely. In fact, we have a divergence with John in that regard because one of the problems with their Antarctic Grace analysis is that the estimate of present-day melting that you get from Grace, from gravity, is very much a strong function of a decontamination that you have to apply for what the Antarctic did 20 to 5,000 years ago. So we think actually that the Antarctic is less of a player than Greenland if we use our ice age model than he does. But within the context of published models, and we can see what that means when we read this IPCC report, I haven't even seen it, these would fit within each of the kind of error bars on the what do they call it, the mass budget of each of those ice reservoirs. Yeah.
The Grace data also have fairly significant seasonal variations, so I think the early papers, you could say they're fitting straight lines to something with a lot of seasonal variability.
Yeah, it's a problem even in my first plot. The main reviewer comment on my plot of showing the free air gravity rate over North America is 4 years, is that really a secular trend? And if I'm going to be fundamentally honest and tell you, look at the trouble you get into not waiting long enough, it may be a problem, right? It may be a problem. Students chair.
Okay, Rose.
Okay, just a quick question. So what is the relative impact of melting of the mountain glaciers compared to these large core ice sheets?
It depends on which observable. So if you're talking about global sea level, then the impact would be extremely large near the ice sheets and away from. Yeah, sure. So you'd have these. Well, I guess this is one advantage of PowerPoint, right? The last time I was here, I don't know if you remember, but my overheads fell off the table. It was quite fun, right, finding them. But this is the Alaskan glacier melting, right? So this zone of a pimple or dimple is a better word than a pimple of sea level change, right, around Alaska. So if you've got, and there's lots of tide gauges monitoring this area, right? So around this area, any global signal is going to be completely dominated by the local drawdown of water associated with Alaska. Now, the answer is different for rotation because those ice sheets, well, they have a small effect on the change in the length of day. And they have almost no effect on polar motion because they're azimuthally distributed, and so they're kind of symmetrically distributed around the poles, so they don't really move it much, right? So sea level locally, very important, right? Yeah,
what about the accumulation of water in reservoirs in the northern hemisphere?
Yeah.
Like as we're melting water, we're also sequestering a lot of water too.
Yeah.
Include any of that?
We don't include it. There's certainly been papers on it. In fact, one of the, well, let me answer the question. The paper suggests on the order of 0.1 millimeter per year as a kind of global measure of the effect. However, of global sea level change associated with the sequestering you're talking about. So that's the kind of rough scale integrated. However, people are now using GRACE data because if you're sequestering that water, just like any of these other processes, will have a fingerprint on sea level. So where you sequester water, you'll have a sea level change that is quite dramatic near that sequestration, right? And so people are looking near areas where they think water is being sequestered, or not, right? Hoping to see the fingerprint of that. So anytime you move mass around, you're going to get one of these sea level fingerprints. So again, just as an answer to Rosemary's question, globally, if you're estimating global sea level change, that sequestration, 5% error it might produce in your estimate. But locally, it could be much larger, right? And so you have to be wary of that, right?
Do you include the melting of the Arctic ice as well as part of Greenland?
In this model? No, we do not. But melting of the Antarctic ice today, if we were thinking about doing this for a very recent event, we would obviously have to, right? But over the last, if we're looking at data over the last 20 or 30 years, most estimates is that Arctic, did you say Arctic ice? Arctic ice is relatively stable over that period, right?
A decrease of the Arctic ice as well.
Yeah.
Like more than Greenland.
In terms of total, I've never seen
This is
estimates.
floating ice.
Oh, floating ice, but that won't have any effect on sea level, right? So changing floating ice, these is all, to have any of this effect, you need grounded ice, right? Right, it was smaller effect. But today, I think the trend is moving away from that, right? There is a mass flux now. And so people are thinking about these ideas in terms of Arctic ice, but not over the longer period of time.
Is there any effect due to the redistribution of mass within the ice sheets? In other words, for example, in Antarctica, thickening in the centre, thinning at the edges. Yeah. In Greenland, more at the north and less at the south. Would that be said to be detectable within the models here?
Very hard. You see, this is. I once gave a talk to a group of sort of altimetry people and said that they're. See, the other way to measure the mass balance of ice sheets is just go and do altimetry and go look. But I dismissed this because ice sheets are such dynamic animals, right, that a measurement in one part of the ice sheet is really not going to tell you much about the bulk properties of that ice sheet. That gets really to some extent to your question. The problem in detecting what you're arguing for, which we've thought about, we've actually done a calculation where we've sort of taken mass from the central core of the Greenland, moved it to the edges where it can then go, right? If you notice, this is a very long wavelength effect, right, if you sort of plotted this out. And so that change, the shift in the possible geometry over a continent the size of Greenland, is really only going to jiggle this a little bit, not enough really to detect, right? But it does jiggle it. And so we had, when we've sort of made these codes available to people so that they can do predictions like this, we give them the freedom to take ice and to not only have a mass flux from Greenland, but also to move ice from one part of Greenland to the other if that's their favored scenario. But we don't think the data is there yet, right?
Speaking of altimeters, you didn't mention anything about ocean altimeters.
Right.
Of course, there are things like Topex beside
Yeah.
you. Does that have any useful
Oh,
information?
Oh, sure. Well, the race is on now to use GRACE data even to look for these fingerprints, right? So if you're trying, the problem, there's a lot of subtle problems in altimeter. Well, altimeters don't look above, they didn't look above generally 60 degrees, right? So they went plus or minus 60. And the problem also in GRACE is that GRACE doesn't see the degree zero change. So it doesn't actually, so you have to think of these maps. Which way did I go? You have to think of these maps and get rid of degree 0 and degree 2, because GRACE doesn't see degree 2 very well either. And these fingerprints actually change. So you have to kind of tailor-make these predictions for the particular mission that you're looking at. And so it turns out that a lot of the signal you get rid of when you get rid of the degrees that GRACE doesn't do very well, right? But people are looking. They're looking at altimeter data for exactly the reason. In fact, Phil Woodworth looked to see whether, and has argued that he sees a difference in sea level change near coast relative to the open ocean, and he's wondering if that isn't linked to a sequestration issue, right? So people are trying to do it. Right?
With respect to the fingerprinting, you showed raw data going up and down and explained why, but the subset of stations all seem to be going up, and then you corrected them. So, right, they're all positive, and yet the previous data, the upper part of the curve, the raw ones.
Yeah.
So is that the absolute value of sea level rates?
Yeah, this is all absolute value.
Oh, it's absolute value.
Right.
Okay, so some of those are actually going up, and some of them are going down.
Yeah. Now look, though you don't want to ever overfit data. I'm not suggesting that this would be perfectly fitting tide gauge data, which is noisy, but it is sort of telling that the two data points we can't fit are San Francisco and Santa Monica, right? And I've done, my master's thesis was on the San Andreas Fault and deformation of North America associated with the fault, which I wanted to talk to you about. And there's certainly vertical motions on transforms. So to argue that you can be around transforms and assume that you're immune to vertical deformation that would corrupt tide gauges, forget it.
The second half of the question was, now that you show how you can fingerprint and fit the data better,
Yeah.
might it point to other tide gauges that you should
Yeah.
start incorporating to actually get a still better fit of the fingerprint?
Yeah, exactly, because A and D, this is a least squares fit, I didn't get into this. I said, and I quickly, as I often do, gloss over these issues, but A and D means Antarctic plus other, right? And the reason that we're stuck there is, let's see this distribution of tide gauge sites, mostly northern hemisphere. So the only way, and mostly near Greenland, and nearly all of these sites, the fingerprint associated with Antarctic would not be visible. You just see kind of a uniform trend here. So unless you have southern hemisphere data, you won't get the Antarctic, ever. So we need coverage here to get it. And that's the only way you break A and D, right?
You remove the glacial ice sag adjustment. Right?
Yeah, or you can do it simultaneously.
But that adjustment, there's a very large spatial variation
Yes.
right through that band of European stations, which must a very long spatial gradient, which must make that very sensitive.
You're arguing that this trend could be explained by a change in the GIA model, in the Ice Age model. Yeah. That's not true, actually. It looks like it would be true. I've actually written a paper. There was this great series of papers published in the mid-90s where people saw trends. Let me show you where the trends really are. I have to go back to the post-glacial sea level change. Yeah, this one. Along this zone here, there are a series of tide gauges, right? That this is a very large peripheral bulge zone here. And so people saw trends in tide gauges, and they corrected for a preferred Ice Age model. And they still saw a trend, and that was all to do, apparently, with changes in the geometry of the ocean currents here. And then what we showed is, no, you could just change the Ice Age model a little bit and get rid of the trends. It turns out that those trends along these European sites, because most of them are actually in this zone here where siphoning is important, are much more immune to changes in the Earth model than you might think. Here, that's not true. The gradients along the US East Coast, in fact, Jim Davis, who Paul knows, and I published a Nature paper saying, reconciling the anomalous tide gauge records along the US East Coast, we said, just change your viscosity, you get rid of all the trends in the tide gauges. But you cannot do that in Europe, right? And that's why, when people, that's why it's an interesting thing that this, there was a great term which I forgot to use, but this, not only was this called geophysical noise, but the fact that European sites showed lower sea level rates than others, and that was immune to any efforts to change the Ice Age model, came to be known as the European problem. That's what they, and they didn't mean that in any geopolitical sense. They just, it's a problem, right? And they called it the European problem, and it even became EP for short, right? And so everyone knew what EP meant. It meant that this was lower than the bulk average there, and there's no way to get rid of it, right? But we don't want to get rid of it because it reflects Greenland.